Okay, so it's a pleasure to be here again. I've been there several times. Yesterday we had an earthquake. Maybe we have trouble with my computer today. So that's okay. So I will speak about these novel forms of silicon. In a sense, this is very similar to at least the first two talks of this morning. But now we are speaking on materials which do not exist in nature. So they are man-made or woman-made, I don't know, okay? And this is purely elemental materials, novel materials, of the column 4, below carbon, giving graphene, which descends from graphite, but below carbon, you have silicon, germanium, tin, lead. And from this, hopefully, you can fabricate, you can design some material which is graphene-like with these elemental materials. Okay, so this is the carbon saga, as you know. So with zero-dimensional fullerenes, the 1D-dimensional carbon nanotubes, and indeed the graphene two-dimensional sheets. And in a sense, what we have done first with silicon instead of carbon follows the same path, more or less, probably by chance, but it's like this. The good thing, as you know, indeed, with graphene physics is the Dirac cone at the K point of the Brillouin zone. Okay. Those Dirac points here. Okay. Last year, the Nobel Prize was delivered for the discovery of the two-dimensional topological phase transition and topological phases of matter. And indeed, this is a very, very promising field. And in a sense, those novel 2D materials, they combine the advantage of graphene topology, honeycomb topology, with the 2D or maybe 1D topological insulator state. Okay, if we go, this is very similar to something that was shown this morning. When you try to continue the downscaling, to prolong possibly the Moore's law, at some point we will face a so-called red brick wall. And essentially, this is to power dissipation issues. And one way, it has been shown already this morning, one way to circumvent this, to mitigate so-called short channel effects, will be to have extremely thin, maybe to the atom limit, atomically thin or just few atom layers channels in a FET. So one candidate could be silicene or germanium or stannine eventually. So these are non-existent to the material which have to be treated, but from theory, and theory started here in Tsukuba by Takeda-san and Shiraishi-san. They were here in Tsukuba when they wrote this paper already 10 years before the advent of graphene. Purely DFT calculation, predicting the possible stage corrugation in silicon and germanium analogs of graphite. We would say now silicene and germanium. And more recently, this was recalculated by Kanjirov et al. And the stability was checked looking at the phonons. And the structure is stable, but at variance with graphene, which is flat, silicene, germanium, stannine are buckled, meaning that the two sublattices, A and B sublattices, are vertically separated by this delta, which is about 0.4 for silicon, 0.6 angstrom, and 0.8 angstrom compared to silicon one-on-one. The hybridization is in between sp2 and sp3, but closer to sp2. From theory, there are many exciting properties which are predicted. Typically, the electrical tunability of the band gap. As I mentioned, these are, in principle, monolayer topological insulators. And it's possible to control even the topological phase transition as shown by Izawa-san. The mobilities are extremely high. If you compare with graphene, for example, you see that the whole mobility for germanium is higher than for graphene. Indeed, all this is for freestanding. I've forgotten to mention. There are also other predictions for non-mediated superconductivity and other mechanisms, possibly of rather high TC superconductivity, but this remains to be proved. These materials, at variance with graphene, which has such a small spin-orbit coupling, just 8 micro EV, that you cannot do anything with that, even though this was first demonstrated for graphene by Kane and Mealy, I think. But if you look at silicon, germanium, and stannning, because the buckling is much higher and the spin-orbit coupling intrinsic is higher, and then there is a synergetic effect, these are robust topological insulators. So the quantum spinel effect is robust up to something like 15, 16 degrees for silicon, nearly a room temperature for germanium, and higher than room temperature for stannine. And indeed, this could be extremely interesting, for example, in this cartoon, to have dissipationless transport on the edge of a ribbon. I like this paper very much. I recommend you to read it, at least the students. In this paper on nanoscience, Roald Hoffen, a Nobel laureate, he has a silicon interlude. It's an interesting story here, but from theory, he thinks that silicon exists, but will be made only on some support, metal or semiconductor. Indeed, silicon is predicted to be less stable than silicon, and we need a special template. And the template we have chosen, this is silver. And the reason comes from my background from the silver on silicon or noble metal on semiconductor system, where silver on silicon makes atomically abrupt epitaxial interfaces. So it was just going to some sort of inverse creation. So let's start from nanodots, zero-dimensional, as the fullerenes in a sense. So we can draw identical, absolutely identical, 0D nanodots like this. They look like this in STM imaging. We discovered them in more than 12 years ago, but we could only solve their structure through extended DFT calculations just last year. And very interestingly, the structure of those nanodots, this is something which is hexacyclic benzene-like with these members, with these arms, silicon here, but they sit on 2 vacancies. Silver is very, very soft. Silver 110 is not reconstructed per se. But if you look at gold or platinum, for example, 1,1,0 surfaces, they are reconstructed 2 by 1 with a missing row. Okay, and this is the trend here. It continues with one-dimensional objects, which are nanoribbons, which at variance with the nanodots that were symmetric, these ribbons break the symmetry. They are all perfectly aligned along the 1,1,0 direction of silver. They have a width of only 8 angstrom. And you see one of the nanodots here. They are grown on silver 111 at room temperature in a massively parallel array. And they display extremely sharp quantum states in angle result photoelectron. This is angle integrated here, photoelectron spectroscopy. If you heat up a little bit, or if you grow at slightly higher temperature, around 200 Celsius, you can grow a nearly perfect array, which is a 5 by 2 along the length, by 5 along this perpendicular direction, the 100 of silver. They can reach hundreds of nanometers in length. They all have the same magic width, 16 angstrom, twice the previous one. So the previous one, we call them single strand. Those one, we call them double strand. And here you see the only defect on this image is a kind of dislocation, disclination. You see here a single strand, it's compensated here, and you see everywhere else the double strand, nanoribbon. This gives this lit pattern. These are obviously one-dimensional objects. In angle-resolved photoelectron spectroscopy, there is absolutely no dispersion perpendicular in this direction. But you have strong dispersion along the length of the nanowires. And especially if you look at this state here, at the corner of the Brillouin zone, if you zoom at it, you see cone-like dispersion with the opening of a gap. Also, after 12 years, we could finally solve their structure. Their structure is really amazing. We thought this would be silicene nanoribbons. This is not real silicene nanoribbons. These are pentasilicene nanoribbons, crystalline nanoribbons, and the tiles are only pentagonal tiles, and they form 1D single-strand crystals or 1D double-strand crystals. You see here the simulated ST image. And by the way, I should mention that a recent paper in POL had just confirmed this structure by surface X-ray diffraction at the synchrotron radiation facility in Grenoble. This is, to the best of my knowledge, the first silicon material composed only of pentagonal tile. There are many pentagons, for example, in cleaved silicon surfaces, or you can find in clathrates or something like that, but they are not purely pentagonal tiles. Here, it is purely pentagonal. So this is the 1D pentasilicene novel material. There are some very recent calculation, PNIS, for pentagraphene. And more recently, for another type of penta arrangement, pentagraphene or pentasilicene-like arrangement. And in 2D, you would have indeed these special states. I still don't know what's happening in 1D, but I hope some theoretician will pick it up. I can maybe imagine that there is even stronger spin-orbit interaction. Okay, now we go to sheets, to 2-dimension. And this is what we observed when depositing at around 200 Celsius only on silver 1-on-1 surface. Now to have the full symmetry. And then we got this image, which is nice. We call it a flower pattern. But this image reveals, in fact, hidden silicene-like symmetry, which is explained here. Indeed, if you look a bit from far in STM imaging, you see a perfect exact honeycomb arrangement, which is a good sign. But this arrangement is too large. In this condition, the arrangement you have, this is a large one here, meaning that 3 protrusions are seen only as one here. But this fits perfectly with a guess of a silicene epitaxial layer. This had to be confirmed. First of all, we did non-contact AFM imaging, and we obtained the same flower pattern, meaning that the imaging condition is governed by the geometry, not by electronic effects. We performed DFT calculations, and we found that this fit perfectly with a 3x3 reconstructed silicene layer matching a 4x4 silver 1-on-1 supercell. And this is the calculations, the minimum energy structure, and this is the STM calculated, simulated image. And why do we have this nice flower pattern? Because in STM imaging or in non-contact AFM imaging, we just image the silicon atom within the honeycomb structure that protrude a bit. And those atoms that protrude a bit, these are those ones that nearly sit right on top of a silver atom. It was very nice, again, from Tsukuba. You know, a lot of good things come from Tsukuba. To have first confirmation of this model experimentally. This was done here in Tsukuba at Keck by reflection high-energy positron diffraction. You need a very high beam of monochromatic positrons that can just surf on the surface. They cannot penetrate. And this, the theory we calculated, and the results are really fantastic. And then very recently, has appeared surface X-ray diffraction study, also I think at the ESRF, confirming exactly our model. Looking at the electronic structure, so we did ARPES at the Soleil facility near Paris. And if you look at the K point of the 1x1 silicene brilliant zone, here you have the SP band of silver. It's very faint here, but you see a cone-like dispersion. And we thought with the opening of a band. Indeed, from calculation, for freestanding, if you extract this silicene reconstructed layer, it should be direct gap with something like, well, 0.2, maybe here it should be 0.6. It's a bit slightly different, but quite okay. Even though very recently has appeared in PNAS by the group of Kowi Hu and co-workers in Beijing, where they have found real cones, you know, up to the Fermi level, at those special points here around the M-bar point of the silver brilliant zone. So we found, in fact, the gaps, apparently gap Dirac point here. They found here so it's still a bit weird, and I don't understand this exactly, but it shows that there is very interesting Dirac physics involved there. What we did also recently, this is a Raman in situ, Raman spectroscopy, to identify the vibration modes. And then we found phonon modes are those oh, I have to go fast, those values, which we could interpret also through DFT calculations. And we could also look at the phase transition to look at the stability. And this monolayer is stable up to around 300 Celsius. And then it collapses in silicon one-on-one crystallites, small crystallites, which are seen in AFM. Functionalization, amazingly, we can functionalize this canonic structure with hydrogen. This is ordered hydrogen absorption. And here, each bump, protrusion, is a hydrogen atom. The 3x3 supercell is preserved, but now there is symmetry breaking, okay? So this hydrogen atom has very special sensitivity to the sublattice. Okay, we can also find other phases, which are, this is the 3x3, 4x4. This is another one which is rotated, more complicated. But it's essentially stretched out, a little bit stretched out silicene. My postdoc was smart enough to identify the 4 domains which are expected for a Ruth-7 by Ruth-7 silicene reconstructed phase matching a Ruth-13 by Ruth-13 silver cell. So you must have by symmetry 4 domains which are seen here. Very interestingly, if you cool down, this is a helium temperature, you find this very weird vortex-like structure, which I believe is due to the fact that silicene has a negative thermal expansion coefficient, while silver has normal 1. So this is stress, creating those vortex-like structure, and in principle, you see the buckling is preserved, but it's changed. This is the flexibility of silicene due to the buckling. And this, in principle, from theory, should support some magnetic moments. Then you could figure out that this is a kind of skyrmion, but this should be calculated. Okay, practical applications, maybe. Colleagues in our European consortium that finance her, with the group of Deja Kivande in Austin, Texas, they managed 2 years ago to make a 2D silicene channel FET. This system, so you can transfer silicene, monolayer silicene. Indeed, it's not very robust for very long. But this was done chemistry, for the, extrusion and everything, and transfer. And then measurement in air, and with some bipolar characteristic, rather good mobilities, if you imagine, for something which is not air resistant more than few minutes. But still, for the first try, I think it's what in French we call a coup de maître. An issue raised by game. Okay, you can read that, With comparative technologies, silicene transistor envisaged in the literature cannot be made. Sorry, they have been done. I've just shown it. But there is a way to do it maybe better, at least to have it safely for longer times. Instead of having just monolayer silicene, you can continue the growth. And the growth proceeds in terraces, okay? All terraces have the same unique structure. This is a Ruth-3 by Ruth-3 in terms of silicene. And recently, colleagues in Australia, in Wollongong, they managed to identify, so this is the Ruth-3 by Ruth-3 unit cell, they could identify the unit block, which is 1 by 1 silicene. And they did also STS, which is, there was some debate. Some people claim that this is just silver-terminated silicon one-on-one. But the STS is totally different, and we have in our past very pronounced Dirac cones with charge transfer, because the Dirac point is around here. Okay. We did also recently surface fixed diffraction measurements. The unit cell is contracted by about 3% compared to silicon one-on-one. It's a different material. The Raman is blue shifted. And if any, we have just very, very little silver on top. This is why maybe this has excited the community. And for example, looking at this Thomson-Reuters citation-based study, the growth and property of silicines has been one of the 10 top hot front in physics, and in fact, #1 in condensed matter physics. Okay, so beyond graphene, we grew silicene. Last year or 2 years ago, we made germanium. And we have in progress, the paper is in preparation, stannine with Junji Yuaran sensei in Nagoya. Prospect, this is what I would like to work on now, the search for Majoranas. In principle, we should have Majoranas at the vortex core when interfaced with an S-wave superconductor. Okay, I have to stop. Just very recent collaborators in different places. I mentioned a group of Yura Sensei in Nagoya, but there are many collaborators in different parts of the world. And I thank you very much for your attention, just leaving you with my summary and conclusions. Thank you.